Hello everyone. Am I audible to everyone?
We can
Ishika,
barely
we
hear
can.
you, so if you can calibrate your mic. Okay. Can you say something?
Hello. Is it
Yeah,
audible now?
it's better.
Okay. I can increase the volume maybe. Is it okay now?
No, there's something in the background. Like
Louder a little bit, but
now,
okay.
There
Can
is
you
some
stop
noise.
it?
Is it better now?
I can hear you, but I cannot see your screen.
Yeah. Now I'm going to share the screen. Yeah. I was just checking the audio. Okay. So I'll share my screen. So is it visible to everyone?
Well, I can see myself. Okay, that's good. All right.
Okay. Okay. So
Okay. Again.
it's visible, right? Okay. So I'll start.
So we have the third talk from the Center for Theoretical Physics. Pleasure to announce Ishika Palit. I'll give you a 2-minute warning time. You have 20 minutes. Please go ahead.
Thank you, Professor Levsniak. So, good morning, everyone. Myself, Ishika Palit, and yeah, I'm doing my PhD here at CFT Pass in Warsaw, Poland. We just heard a very nice talk from my supervisor, Professor Januk. And now I'm going to talk about modeling of wind-fed accretion in high-mass X-ray binaries using a GRMHD code, the same one Beston and Professor Januk talked about. So let me start. This is the rough plan of my talk considering the time limit. I'll start with a brief introduction to X-ray binaries. So, um, yes, so X-ray binaries consist of a normal star and a collapsed star, which could be either a white dwarf, neutron star, or black hole, orbiting around their common center of mass. These pairs of stars produce X-rays if the stars are close enough together that the material is pulled off the normal star by the gravity of the dense collapsed star. The X-rays coming from the area around the compact object where the material that is falling toward it is heated to a very high temperature. Depending upon the mass of the companion, these binaries can be roughly classified into two categories: low mass X ray binaries and high mass X ray binaries. Now, the high mass X ray binaries are observed to be more brighter source of X rays, and the reason is believed to be due to the presence of a very hot corona. Matter can fall onto this compact object either through Rorschach overflow or direct impact of a stellar wind. So, to summarize with some sketches, high mass X-ray binaries have massive companions, mostly O or B type stars, which are associated with strong stellar winds, whereas low mass X-ray binaries have less massive companions, mostly K or M type stars. So, material for accretion in high mass X-ray binaries are mostly wind fed, whereas accretion proceeds in low mass X-ray binaries mainly when the companion star fills its Rorschach during its stellar evolution. Now, the Rorschach is the name of the region around a star in a binary system within which orbiting material is gravitationally bound to that star. Okay, so moving on to our topic of interest, that is Cygnus X-1, let me discuss a few of its features and its wind. It's a high mass X ray binary with a black hole, namely Cygnus, and a companion named HT226868, which is in between O and B type star. This is a plot of flux over energy showing the observed spectra of Cygnus X-1, and it can be seen that the observed spectra is combined contribution from the accretion disk as well as the hot corona. The system is either in the hard state, in which the Comptonized power law component dominates, originating in a hot optically thin plasma, or in the soft state, dominated by the cooler thermal disk component. Sometimes the transition from the hard to the soft state is not fully performed, and the source remains in the intermediate state. The observed X-ray variability of Cygnus X-1 is most likely a combination of the propagating perturbations. appearing at some characteristic radii of the hot flow. This is another observation showing spectra of Cygnus X-1, and in spite of the high intrinsic variability, the high state during June, July, and August can clearly be distinguished. An important variability component is due to the variable stellar wind from the companion. Uh, the driving mechanism of stellar wind in Cygnus X-1 is due to radiation pressure. Mostly all hot stars have winds driven by radiation. The basic mechanism driving the winds of hot stars is the transfer of photospheric photon momentum to the plasma and stellar atmosphere through absorption by spectral lines. The properties of stellar wind depend on the number of lines being able to absorb significant amount of photon momentum. So the perturbations in the stellar wind cause variations in the parameters of the flow, such as density, velocity, and temperature, which compresses the gas into small and cold and overdense structures, often referred to as clumps. This is a sketch from Hirsch et al. 2019, which shows the clump passing our line of sight and causing the different dip stages. Red color indicates more highly ionized region, and the blue color region indicates lower ionization balance. These clumps are stated responsible for the observed absorption dips, that is, the lower flux in the hard state spectra. This figure shows the strong dip spectrum from observation of revealing emission lines from the photonized zone around the black hole. So, to summarize, the stellar wind that is powering the accretion in the system is characterized by temperature and density inhomogeneities, including structures or clumps of colder, more dense material embedded in the photonized gas. As these clumps pass our line of sight, absorption dips appear in the light curve. So now I will describe my model setup. This is our model replicating the wind-fed accretion scenario of Cygnus X-1. The clumps are coming from the focused wind from the companion star at the outer boundary of our computational grid. The prescription of density at the outer boundary is estimated from the previous studies regarding clump mass and density. We implement function generating values between the prescribed maximum and minimum amplitude of the density. Um, these estimated values are at first converted from physical units to the dimensionless code units in order to prescribe in our simulation. Um, the choice of maximum and minimum of angular momentum is such that the matter has angular momentum adequately higher or lower than the value at the marginally stable orbit, representing very fast and very slow rotation, respectively. These are the plots for density and angular momentum changes at the outer boundary throughout the evolution. If you can see the x-axis, it's the time scale, which is still 100 seconds. That's our whole time of evolution of the simulation. Also, the zoom plots are added to show the distribution of these quantities at the outer boundary. Now, my initial conditions include quasi-spherical distribution of gas, inviscid non-magnetized flow, polytropic equation of state, and transonic accretion model, which includes the shock solution. The word transonic means relating to speeds to the speed of close to that of sound. Thus, the pressure waves in the accretion flow traveling with sound speed will give us the local sound speed, like equal to pressure into adiabatic index by the density. Mm, so now to explain what I mean by shock solution, shock develops in the flow when supersonic flow is obstructed. Now the location of shock can be derived using the basic hydrodynamical flow equations, the mass conservation equation, the integrated from the continuity equation, and the energy conservation equation integrated from the radial momentum equation. Um, Further, with the proper substitutions and inserting the value of local sound speed, AC, into the energy equation, we get this polynomial expression which gives the critical points of the flow. So a critical point RC can be seen here as a function of epsilon, lambda, and gamma. That is, the critical points in the flow depends on the specific energy, specific angular momentum, and adiabatic index of the flow. Thus, with such initial conditions, solutions are generally transonic, and both smooth transonic solutions and solution with shocks exist, depending upon the adopted parameters of the flow. There are many studies by Das et al. 2003, Das and Cherny in 2012, and many references therein. So here we focus on the solution with shocks. Um, now, let me try to explain all the shock with the help of a figure. So we have a hot supersonic flow, the blue one, entering into the black hole. Now, close to horizon, matter starts feeling a centrifugal barrier, and along with the pressure waves, matter virtually stops, causing a shock in the flow. Thus, in the hot, puffed up, geometrically thick structure, hot gas pressure and the centrifugal force together balances the gravitational force. This slows down the fall and flow becomes subsonic, the pinkish one. And after a while, the gravity dominates again and the matter enters into the black hole supersonically. So the left figure is an equatorial slice showing the three critical points in the flow. Now, moving on to the numerics, we use the code HARM for our numerical simulation, which stands for high accuracy relativistic magnetohydrodynamics. And HARM, it is a conservative code with shock capturing schemes. HARM follows the dynamical evolution of GRMHD equations, and this is achieved by solving the continuity equation, the four momentum energy conservation equation, and induction equation in GR framework numerically. The stress energy tensor includes both the components, T mu nu gas and the T mu nu electromagnetic part. But we have considered non-magnetized flow, so the induction equation and the electromagnetic part of the stress energy tensor is not included here in our model. Now let me say a few details about implementation in the algorithm in the code. So in two dimensions, we need to evaluate G mu nu contravariant and covariant components and the metric determinant at 4 points in every grid zone: the center, two faces, and one corner. And metric connections, the Christoffel symbols at the zone center. It would be difficult to accurately encode analytic expressions for all these quantities. So HARM is coded so that an analytic expression needed only to be provided for G mu nu, and all the other geometric quantities are calculated numerically. For example, the Christoffel symbols is obtained to sufficient accuracy by numerical differentiation of the metric. Um, yeah, so this minimizes the risk of coding errors in specifying the geometry in the code. So it also minimizes the coordinate dependence and making it relatively easy to change coordinate systems. Another thing is about this negative densities and internal energies, which are forbidden by the GRMHD equations, but numerically nothing prevents their appearance. So in fact, negative internal energies are quite common in numerical integration with large density or pressure contrast. So following the common practice, HARM prevents this by introducing the floor values for density and internal energy. These floor values are enforced after half step and the full step. So now HARM solves the GRMHD equation in Kerr-Shield coordinate system. So we don't face problem regarding the coordinate singularity, and matter can flow smoothly through the horizon. The integrated equation are of the form this, and where U is a vector of conserved variables such as particle number, density, or energy or momentum. Fi are the fluxes in the finite volume. Yeah, and S is a vector of source term. U is conserved in the state that sense that if the source term is zero, it depends only on the fluxes at the boundaries. The vector P is composed of primitive variables such as rest mass density, internal energy density, velocity components, and magnetic field components, which are interpolated to model the flow within the zones. So the time step of this conservative scheme works like this. We put the initial condition, which calculates the flux, updates the conservative variables. Further, the primitive variables get updated for the next time using the conserved variables. And now moving on to the boundary conditions in HARM. So the default boundary condition has a free inflow outflow, but we have added further choices in the boundary conditions in the code. The code with outer boundary condition have a fixed density was used to study parameter space for the shock formation in one of our earlier studies. And we use the time varying outer boundary condition to study wind fed accretion and Cygnus X-1. So now I will move to my results section. So here I show some movies for various quantities such as Mach number, angular momentum, density, and radial velocity, showing changes at outer boundary throughout the evolution of the flow till 100 seconds. So the changes at the outer boundary can be seen for these parameters. And here on the right hand side, the plots of angular momentum are zoomed in close to horizon, showing the difference in the profile for the models with wind and without the wind. So the blue one is the model with wind and the green one is without wind. And now these are some 2D snapshots of various quantities such as Mach number, angular momentum, and density on the left hand side. And on the left hand side too, there's the plot of the shock, so these quantities are showing the shock growth of the growth of the shock in throughout the evolution. So I have selected a particular time to three different times to show the growth of the shock bubble. The top right figure is the oscillatory shock we have in our flow throughout the evolution. And the bottom right figure is the plot at the similar time shots as these quantities, showing the velocity field lines when the shock shrinks and grows back. So the field lines can be seen pushing the shock outward, making it grow bigger, and again pushing it inward to make it shrink. And this keeps going on throughout the evolution. And now these are the mass accretion rate calculated at the inner radii, that is 3 gravitational radii. And this one is the lower one is the mass accretion rate at the outer radii. The right figure is the power density spectra calculated from the mass accretion, the light curve we choose as a mass accretion rate at the inner radii. And the PDS are further binned logarithmically. So now we wanted to compare our results with the observational data. And we found that our simulated PDS matches the observed spectra quite nicely. Further, we did Lorentzian fitting of our data to get the peak frequencies of the variability. We used the same formula as Pochmet et al. 2003 to calculate the Lorentzians. And we see that the model with wind affects predominantly the lowest frequencies, below 1 Hertz, while the higher frequency, which are originating closer to the black hole in the flow, are by itself. So their appearance is related to the shock formation in the low angular momentum flow. The major difference can be seen in the first Lorentzian, which represents the oscillation at larger radii. The chi-square values are higher in our model due to very small statistical errors in the high frequency part in the PDS. They are actually dominated by the highest frequency point. So below 100 Hertz, the deviations in the individual bins are of order 2 sigma or smaller, very similar to the data residuals shown in Pochmet et al. Our peak frequencies are also very close to the observed ones from Pochmet et al. 2003. Another recent observational analysis by Accretion and Dawn also estimates these 3 peak frequencies from their study, and they are also in close range to our values. This figure from their article shows roughly the location of the respective Lorentzian in the hot flow. So unlike them, we don't have any thin disk, but only the hot coronal flow in our models. So before ending, I'll add a few comments on our results. We have not included emissivity properties of hot medium, so we are not able to address specific emission components, but we do follow all the aspects of propagating fluctuations. Our time dependent evolution of the hot flow does not yet include the interaction of with the cold disk, which likely overlaps with the hot flow at some range of radii, even in the hard state. And the shock formation in our flow, which is responsible for angular momentum transport, is a very parameter specific feature. So I will conclude my talk stating that we found our low angular momentum coronal accretion model is able to represent the propagation of perturbations from the outer boundary and explain the variability pattern seen in the hard state of Cygnus X-1. So thank you for your attention.
Thank you. So we have time for questions.
So do you have any preprocession, for example, for lines, for separate lines?
Sorry, can you repeat?
So if you would like to get some lines from your results, when you would like to address the emission, you would have to use some preprocession, or how you would
post processing. Actually, yes. So right now we don't have such properties, but we have that in plan with Dr. Venda Zhang. So he has some kind of models to calculate this emissivity properties and then to have the actual light curve to process the PDS. But yeah, for now we don't have that. So we just consider our mass accretion rate varying with time to calculate all this PDS.
Okay, but you will get. So now you will make models. I mean, you will get some results, and then later you will pre-process it. Yes, and you will get from those results. There could be some further results, which will show the lines. Yes.
Yeah, the to say like the actual light curve, maybe like through the whole flow, integrated throughout the flow. Yeah.
Okay. Thanks, Sarah.
Do you have any other questions? If not, let's thank the speaker once again.
Thank you.
All right. And back to the organizers. I believe this was the last talk of the session.